Okay. All right. So today, what we're going to do is to continue on our discussion, and we're going to talk about tangent planes and differentials. So, in this section, again, um, we're going to do kind of an extension of what we did with vectors, and as far as like writing planes and stuff, but we are going to deal with functions. So, we're going to be utilizing derivatives. Okay. So, one of the first things we're going to deal with is the formula for a tangent plane. So if we have a function that is defined as f of x, y, z, and it's equal to c, and we have it at a point x sub 0, comma, y sub 0, comma, z sub 0, okay? So we are able to write an equation for a plane, and an equation is going to look like this. We're going to take the partial with respect to x, evaluated at p sub 0, times x minus x sub 0, plus partial with respect to y, evaluated at p sub 0, times y minus y sub 0, plus the partial with respect to z, evaluate the point p sub 0 times z minus z sub 0, and this is going to be equal to 0. Okay? So this will be representing the tangent plane. Okay. All right. Now, if we want to do what we refer to as a normal line, okay, for the function f of x, y, z is equal to c at the point x sub 0, comma, y sub 0, comma, z sub 0. So if we want to do that, it's going to look like this. Now, when we write the equation for the normal line, we're going to write it in parametric form. So we're going to have that x is equal to x sub 0 plus partial in respect to x, evaluate at p sub 0 times t, comma, y is equal to y sub 0 plus the partial in respect to y at p sub 0 times t. And then finally, we have that z is equal to z sub 0 plus the partial of f in respect to z at the point p sub 0 times t. Should put zeros here. Okay. Any questions? Okay, so next we have one more formula that we're going to deal with, and this is going to be a plane tangent to a surface. Okay, so plane tangent to the surface, f of xy at the point, left out just a little bit, z equals f of xy at the point p sub 0 defined at x sub 0, comma, y sub 0, comma, f of x sub 0, comma, y sub 0. Okay, so for this, our our equation is going to look like this. So I'm going to take the partial in respect to x, evaluate it at x of 0, y sub 0, times x minus x of 0, plus y partial in respect to y, evaluated at x of 0 comma y sub 0, and then multiply that by y minus y sub 0. Then we're going to do minus z minus z sub 0, and that's equal to 0. Now, kind of the reasoning behind why this is going to be a negative, basically -1 times this, because if we take this equation, so if we have the equation and rewrite the surface, which is z is equal to f of x, y, okay? So if we rewrite it and say that it's f of x, y minus z is equal to 0. So if we take the partial of this in respect to z, we're going to end up with a value of -1. So it's basically looking at the first formula. But since the function is not defined in terms of z, we bring z over, have it equal to 0, and then we'll do the partial. We're get like the slope is going to be -1. So that's why the negative z minus z sub 0 is at the end of this, when you have it defined only, the function defined only in two variables. Any questions there? Okay. All right. So let's take a look at some examples and show you how this is going to work. All right. So our first example, we have this. We have our function defined as x squared plus y squared minus z squared is equal to 18. And we're given a point of 3, 5, and -4. Okay, so for part A, what it wants us to do is to find an equation of a tangent plane at p sub 0 on the given surface. Okay, so basically what we're going to do first is that we need all the partials. So if I do the partial of f in respect to x, what is that going to be equal to? Okay, so we're going to have 2x. Now, if I evaluate the partial in respect to x at point p sub 0, what value will I get? I get 6. Okay, so now let's do the partial in respect to y. What value? Get 2y. And if I evaluate it at p sub 0, I'm going to get what? 10. And then let's do the partial in respect to z. What will I get? -2z. And then if I evaluate that at p sub 0, what value will I get? 8. Okay, so these numbers here are going to be our numbers that are in front. Okay, so what we're going to have is 6 times x minus x of 0, which is going to be 3, plus 10 times y minus y sub 0, which is 5, plus 8 times z minus z sub 0, which is -4. So we're going to end up with plus 4 is equal to 0. Okay. Now, technically, this is a solution, but we normally don't leave it in this form. So we'll clean it up a little bit. So if we distribute out, we're going to end up with 6x minus 18 plus 10y minus 50 plus 8z plus 32 is equal to 0. Or we end up with 6x plus 10y plus 8z. We're going to end up with minus, we have 68 and 32, which is going to give us 36, is equal to 0. All right, so this is one way to represent the solution for the tangent plane, or you could write it as 6x plus 10y plus 8z equals 36. Okay, so either one of these is correct. Any questions there? Okay. Now, part B of this is basically asking us to write an equation for a normal line to this. And again, when we write the equation, it is going to be in parametric. So we're going to have that x is going to be equal to x of 0. So that's the x coordinate of the point, which is 3, plus, then we're going to use the slope value from the partial in respect to x, and we said that value was 6. And then don't forget t. Then y is going to be equal to the y coordinate of the point, which is 5, plus the slope value evaluated, the partial y value at the point, which is 10. And then z is going to be the z coordinate of the point, which is -4, plus then the slope and then t. So we're going to have 8t. Any questions there? All right, let's look at our next example. So next example, we are given an equation that x squared minus xy minus y squared minus z is equal to 0. And our initial point, our starting point is 1, 1, -1. Okay. So again, part A, we're going to write an equation of a tangent plane. All right. So what would the partial of f in respect to x be? All right. So we're going to have 2x minus y. And if we evaluate that at p sub 0, what will I get? Get 1. Okay. So next, let's find the partial in respect to y. All right. So we're going to have negative x minus 2y. Now, if I evaluate that at p sub 0, what will I get? -3, good. And then if I do the partial in respect to z, what will I get? I get -1. And if I evaluate a p sub 0, I'm still going to have -1. Okay. All right, so if I write my equation for the plane, I'm going to have 1 times x minus 1 minus 3 times y minus 1 minus 1 times z plus 1, and this is equal to 0. So if I clean this up, I'm going to have that x minus 1 minus 3y plus 3 minus z minus 1 is equal to 0. So I could say that my final answer would be that x minus 3y minus z would be equal to what? -1. Okay. Or Again, you can have the negative 1 on the other side, so it'll be plus 1 is equal to 0. Okay, so you can have it either way. Any questions? Okay, so next, let's look at part B. So part B, we're going to write an equation of a normal line. So we're going to have x is equal to, all right, so the x coordinate of the point was 1. And what was the slope for the partial of f in respect to x?
1.
Okay, so we're going to have plus just t. So y is going to be equal to 1. And then what was the partial of y in respect to the point? What was that again?
-3.
Thank you. And then, hold on one second. Turn my volume up a little bit. All right, so z is going to be equal to, what would that equation be?
-1, -t.
Okay, so -1 minus t. Any questions there? Okay, so as you notice with these problems are pretty straightforward. You just got to make sure, one, that you do the partial correctly, and two, make sure that you evaluate correctly. Okay. All right, next example. So suppose that we are given the equation um, of a surface, which is defined as z is equal to e to the negative x squared plus y squared, and we're given the point 0, 0, 1. Okay? And we are asked to write an equation of a plane that is tangent to the given surface. Okay, so in order to do this, basically what we need to do is to find all the partials. So, and really we only have to do two partials. So if we do the partial with respect to x, what would that be?
-2x e to the power -a squared plus 1 squared.
Okay, so that will be that partial. Now, if we evaluate it at 0, 0, what will we get?
0.
Okay, we're going to get 0. Okay, now next we're going to do the partial in respect to y. So what would that be?
-2y e to the power -a squared plus 1 squared.
All right, and if we evaluate the point 0, 0, what are we going to get?
0.
Okay, now when we look at this, we basically are going to have that 0 times x minus 0 plus 0 times y minus 0 minus z minus 1, and that's equal to 0. Well, what happens is that those are gone because there's 0. All right, so essentially what I'm left with is negative z plus 1 is equal to 0, or I can say that z is equal to 1, and that would be the equation of the plane tangent to the surface. Any questions? Okay, so let's look at another example. All right, so this time we are given the plane that z is equal to 4x squared plus y squared, and we have the point 115. Okay, so first, what I want to do is find the partial with respect to x, and that's going to give me what?
AX.
Yes, 8x. And if we evaluate it at the 0.11, what do we end up with?
8.
Okay. All right, next we're going to find the partial with respect to y, and what will we get there?
2y.
And if we evaluate it at the 0.11, what are we going to end up with?
2.
Okay. All right, so now we're ready to write our equation. So it's going to be 8 times x minus what?
1.
Plus 2 times y minus what?
1.
Minus z minus 5. Okay, and this is equal to 0. And again, basically what we're going to do now is just clean it up a little bit. So we're going to end up with 8x minus 8 plus 2y minus 2 minus z plus 5 is equal to 0. So we can say that 8x plus 2y minus z is going to be equal to what?
5.
And there we go. Any questions? What do you mean simplify further? Oh, no, you don't have to do that. No. Typically with a plane, you want all the variables on the same side. No problem. Any other questions? Okay, so next, what we want to do is, in the next example, all right, we're given two surfaces. We're told that one surface is defined as x plus y squared plus z equals 2, and the other surface is y equals 1. And we're given a point of 1/2, 1, 1/2. So now what we want to do is define a parametric equation for the line tangent to the curve of intersection of the surfaces in the given point. Okay. So, in order for us to do this, all right, here's kind of the series of steps of what we're going to do. All right. So the first step is we're going to find the gradient of f. Okay. So we're going to consider the function with all the variables f. Okay. So if we do the gradient of f, that means that we need to find the partial in respect to x in the I direction, plus the partial in respect to y in the j direction, plus the partial in respect to z in the k direction. Okay, so what would be the partial in respect to x? Okay, so we have 1 in the I direction, plus partial in respect to y, 2y in the j direction, plus the partial in respect to z. It'll be 1 in the k direction. Now, once we found the gradient, we're going to evaluate the gradient at the given point. So if we evaluate the gradient at the given point, we're going to end up with 1 in the I direction plus 2 in the J direction plus 1 in the K direction. Any questions there? All right, now the second function is going to be considered G. Okay, so what we're going to do next is to find the gradient of G. Okay, so that's going to be the partial in respect to x in the I plus the partial in respect to y in the j plus the partial in respect to z in the k. Okay, so if I do that, what will I end up with for the gradient of G? Right, I'm going to end up with 1 in the j direction. Okay, now if I had variables in it, then I would evaluate the gradient of G at the point. But since it's just a numerical, I don't have to do that step. Okay. Now, let's think about this. Okay. If we're trying to determine if something is try to do something at an intersection, what should we do with two vectors? Yes, we're going to do the cross product. So that's kind of the next step that we're going to do. So we're going to do the cross product of the gradient of f and the gradient of g. Okay, and keep in mind that these are evaluated at the point. Okay, so if we do this cross product, we're going to have our I, J, K components. All right, for f, we had it to be 1, 2, 1. For g, it would be 0, 1, 0. Okay. All right. So now for the ith component, it would have a coefficient of what?
One.
Careful.
It's gonna be -1, right?
Right. Okay. Minus for the j component, it will have a coefficient of what?
0.
Okay. And then for the k component, it's going to have a coefficient of what?
1.
Okay. All right. So now what we're going to do is to write our equation for our tangent line. Okay. So equation of our tangent line. So we're going to write in parametric. So x is equal to x of 0 plus our slope at t. Okay. So if we do this, we're going to have that x is equal to, what is x of 0 going to be? Yes, it's going to be 1/2 because it's based on the point. Plus, what's our slope going to be? It's going to be -1 times t. Or simply we will write 1/2 minus t. and that will be our equation for the x portion of the parametric. All right. What would be the equation for the y portion of the parametric? Y equals 1, yes. Okay, because our slope is 0, so we know we're not going to have a t. And then for the z portion of the line, what would that equation be? Yes, that's going to be 1/2 plus t. Okay. Any questions? So now, let's take a look at another example. Okay. All right, so this example, we're asked by about how much will h of xyz equal to the cosine of pi xy plus x z squared change if the point P, which is defined as xyz, moves from P sub 0, which is -1, -1, -1, to a distance of d sub s 0.1 units toward the origin. All right, so what we're going to do with this, okay, we are going to start off with our equation, our function, which is defined as the cosine of pi xy plus xz squared. Okay, so the first thing we're going to do with this in order to help us is we're going to find the gradient of h. So step one, what we're going to do is to find the gradient of h. All right. So if I do the gradient of h, that means we're going to do the partial of h in respect to x in the I direction plus partial of h in respect to y in the j direction plus the partial of h in respect to z in the k direction. Okay. So for the I direction, what are we going to have for the partial in respect to x?
Negative pi y.
Negative pi times what?
Y.
Yes. Let me write that a little clearer, better. Hold on 1 second. We're going to have negative pi y. Okay, keep going.
Sine pi xy.
Okay.
In the I direction.
You're missing some. Yes, plus z squared. And that's going to be in the I direction. Okay. Plus, what's the partial of h in respect to y?
Negative pi x.
I'm going to wrap this around, so it's going to be negative pi x times.
Sine pi xy.
Okay. All right, and that's going to be in the j direction. Plus, all right, so what will be our partial respect to z?
2z. 2xz. Right.
2xz in the k direction. Okay. Any questions there? All right, so now once we found the gradient, we're going to evaluate the gradient at the given point. Now, the given point that they gave us in this problem was -1, -1, -1. Okay, so if we evaluate the given point, we're going to end up with pi times the sine of pi in the, oops, hold on, left out a little bit, plus 1 in the I direction, plus, and then we're going to have pi times the sine of pi in the j direction, plus 2 in the k direction. So now, once we do this, we're just going to clean this up. So for the I component, what would the coefficient be? Yes, it's going to be 1 in the I direction, plus for the j component, it's going to be what?
0.
0. And in the k component, we know what that is. It's going to be 2 in the k. Okay, so here's our gradient of h evaluated at the point. Any questions? All right, so next, what we're going to do, okay, so the first part is just dealing with what we have and coming up with the gradient of h at the point, the given point. All right, so next, what we need to do is to create a unit vector. Okay, well, we can, and let's not call it a unit vector. Let's call it a vector v. Okay, so what we need to do next is to find a vector v. All right, so to help us with this vector v, keep in mind that we can create a vector using 2 points. Okay, so we have that one point was given to us, and our p sub 0 was -1, -1, -1. Okay, now we need to find a second point. Now, based on the information from this problem, what could the second point be?
One zero two.
No, can't be that. It's something that is set. So if you read the problem, we're moving towards something.
The origin.
We're moving toward the origin. So that would be our second point. Okay, so we're going to use the point 0, 0, 0. Okay, so now our vector v is going to be basically the vector form from p sub 0, p sub 1. Okay, so if I create this vector, All right. I'm going to have 1 in the I direction plus 1 in the J direction plus 1 in the K direction. Okay. So now I've created a second vector. All right. Now, with this vector that I just created, I need to find the unit vector. Okay. So our unit vector is going to be vector v over the norm of vector v. Okay. So vector v, the norm of vector v would be what?
Why in the I direction?
The norm of vector v?
Oh, sorry. Why in the I direction?
No. What's the norm of vector v?
Oh no,
What's the
sorry.
magnitude of vector v?
√3.
There we go. So we're going to have 1 over the square root of 3, and then we're going to times it by vector v, which is I, j, and k. Okay. All right. So what we're going to do now is what we're trying to do is to estimate how much h changes. So what we're looking for dH. Okay. And dH is going to represent the differential, or it does it represents the change in h. Okay. And not respect anything. That's the whole concept of a differential. The differential is just looking for the change of that particular function. Okay. Now, in order to find this change in h, what we need to do is we're going to take the directional derivative. Okay. And we're going to multiply it by the change in distance for, in this case, ds. Okay. So we're going to take the directional derivative times the change in s, and s is dealing with how it's moving toward that point. Okay. So here's how we're going to do this. All right, so we're going to have that dH is equal to, now the directional derivative that we're going to be dealing with, so we're going to be dealing du of h. All right. Now, keep in mind that we do want to, and then we're going to times that by ds. Now, to find this, it's basically the gradient. Let me clean up what I'm writing. So it's going to be the gradient of h evaluated at p sub 0 dotted with the unit vector. And then we're going to multiply it by ds. Okay, so for this, the gradient of h evaluated at the point, we came up with the value of, and I'm going to do it in just the coordinate form. So we had 1, 0, 1, 1, 0, 2. So we're going to dot that with the unit vector. Well, the unit vector is defined as 1 over the square root of 3 times 1, 1, 1. And then we're going to multiply that answer by ds, which is defined as 0.1. Okay. Now, when we're doing the dot product, a constant can be pulled out. So the 1 over square root of 3 can be pulled out. And we're going to multiply by. All right, so we're going to have basically, when we do the dot product, we're going to have 1 plus 0 plus 2. Okay, and then we're going to multiply that by 0.01. Or essentially, we're going to end up with 3 over the square root of 3 times 0.1. Okay. And we can do an approximation of this. So we're going to get approximately, I'm going to round it to 4 decimal places, 0.173. Okay. So this is the rate that H is changing as the point moves toward the origin at a rate of 0.1. Any questions?
Yeah, Professor, when we do problems like this, is it always going to be an approximation or will we have exact numbers sometimes?
Normally, when you're dealing with something like this as a rate of change, you're probably going to end up, the only way that I can think of is whenever you find the unit vector, if it comes out nicely. If the unit vector does not come out nicely, then it's probably going to be an approximation, especially since if you have the square root of something in there.
Yeah, thank you.
Any other questions? Okay, so the next thing I'm going to talk about is dealing with linearization. Okay, now linearization is basically it's a way of using a tangent line to approximate a value on a curve. Okay, now linearization, I taught it many years ago. I used to teach it always in Calc 1, just to show students how linearization worked and everything. But we typically don't teach it in Calc 1, but it is in a way to approximate, do an approximation for a value on a curve using tangent line. Okay, now we are going to use it now because it does make sense to do it in terms of when you start dealing with multiple variables, okay, to do that. Okay, so our formula that we're going to use is for linearization. Okay, if we have L of xy, and this is going to be equal to, we're going to evaluate the function at f of 0, y sub 0. Then we're going to add, then we're going to do the partial with respect to x, evaluate it at the given point, and then multiply that by x minus x of 0, plus partial with respect to y, and we're going to evaluate it at the given point, and then times y minus y sub 0. Okay? Now, the bigger this, if you add more variables to this, basically just adds another partial and then the next variable minus its starting point. So again, it's just a way of doing approximations. All right. Now, basically, what happens here is that if you are doing the approximation close enough to the curve with the tangent, if the point's close enough to where the tangent touches the curve, then we can say that the value of f of xy is going to be approximately what the value of the linearization at xy would be. Okay, so let me show you how this is going to work. All right, so what we're going to do is we're going to do an linearization for a function, and we're going to do it at two different points. Okay, and you'll see how it affects the how it affects the equation of the linearization. All right, so for the first example, I have this, and I may have fixed this in the notes, but I can't remember. The equation should be x plus y plus 2 squared. It may be still z. Hopefully I fixed that file, but in case I didn't, it should be that. Okay. All right. Yeah, it should be 2. It shouldn't be z. All right. So the first time, we're going to look at the point 0, 0 and create a linearization. So if we do that, our linearization is going to be equal to, we're going to look at f of 0, 0 plus the partial with respect to x of evaluated at 0, 0 times x minus 0 plus, then we're going to do the partial with respect to y evaluated at 0, 0 times y minus 0. Okay, and this is going to create our equation. So now, if we take a look at our function, all right, so if we evaluate our function at 0, 0, what do we get? We get 4 plus, okay? So now, if we take the partial in respect to x, what will we get? So we're going to have 2 times x plus y plus 2 times 1. And if we evaluate that at 0, 0, what do we get?
4.
Okay, so it's going to end up being 4x plus, if we do the partial in respect to y, it's going to be the same derivative, okay? And if we evaluate it at 0, 0, we're going to get what?
Or y.
We're still going to, yeah, 4y. So this will be the approximation at the point 0, 0. Okay. Any questions there? So now let's move the point. Okay. So in part B, we're going to move the point, and we're going to move the point to 1, 2. Okay. And now we're going to do a new linearization formula for this. Okay. So we're going to look at f of 1, 2 plus the partial with respect to x at 1, 2 times, this time it's going to be x minus 1 plus, then we're going to do the partial with respect to y at 1, 2, and then it's going to be y minus 2. Okay. Now, if we evaluate the function at 1, 2, what value do we get?
25.
Okay. Plus, if we evaluate the partial with respect to x at 1, 2,
0.
okay. Is it going to be 0? at 1, 2?
I mean, the first term will get the number 10, and the second one would get 0, right? X minus 1. Oh, oh no, wait.
Did you get 10 both times?
Yeah, I mean, for the f of x 1, 2, I get 10, and then the second.
Okay. So f of y 1, 2 should also get 10. Because it's going to be the same derivative. So did everyone get 10 for both f of x and f of y at 1, 1, 2? Okay. Yeah, so it should be 10 for both of those partials evaluated at 1, 2. Okay. All right. So basically, if we clean this up, we should end up with 10x plus 10y. And if we combine the constants, I think we should get -5 for that. Okay. Any questions there? Okay. All right. So the next thing we're going to do is we're going to do linearization and we're going to look at the error that's going to reproduce. But before we dive into that, let's take a short break. So let's do a 2-minute break and come back at 12:10, and then we'll talk about that problem because this problem is a little bit longer than what it looks. Okay. Okay, so let's look at our last example. So the last example is asking this. This is find the linearization L of xy of the function f of xy at p sub 0. Then find an upper bound for the magnitude of the error um, in the approximation of f of xy approximating the linearization of xy over the rectangular region. Okay, so in this problem, we are told that the function f of xy is defined as x times y squared plus y times the cosine of x minus 1. And at the point p sub 0 is defined as 1, 2. Now, our region is going to be a rectangular region, and it is y, excuse me, not y, but x minus 1 is less than or equal to 0.1, and we're told that y minus 2 is less than or equal to 0.1. Okay, so again, one of the first things we want to do is we want to do the linearization. Okay, so to do the linearization, we need to find f of 1, 2. Okay, so if I evaluate the function at 1, 2, I'm going to end up with 4 plus 2 times 1, or 6. Next, I know I'm going to need the partial of f in respect to x. And if I do that, that's going to be y squared minus y times the sine of x minus 1. Now, I want to evaluate that at the point 1, 2. And when I do that, I'm going to end up with 4 minus 2 times 0, or 4. And then I want to find the partial of y, partial of f in respect to y. Let me say that correctly. So I should end up with 2xy plus the cosine of x minus 1. And again, I want to evaluate at the point 1, 2. So I'm going to end up with 4 plus 1, or 5. So my equation for my linearization, L of xy, is going to be equal to 6 plus 4 times x minus 1 plus 5 times y minus 2. Or I can write this as 4x plus 5y. What do we have? Minus 8. Okay. And this will be our linearization. Any questions there? Okay, so the next thing I'm going to do is to take a look and see what we're dealing with as far as the region is concerned. Okay, so I'm going to do kind of a rough sketch of what the region would look like. Okay, so, and I'm going to blow it up just a little bit. Okay, so let's say this is 1 and this is 2. So here's our start here. Now, basically saying the absolute value of x minus 1 is less than or equal to 0.1. Okay, so what that tells me is that we can go 0.1 units on each side on x. So we can go over to here, and this will give us 1.1. Or we can go over to here, and this will give us 0.9. Okay? And then on y, we can do the same thing. Okay? So we'll be able to go up 0.1. So we get 2.1, go down 0.1, and that'll give us 1.9. And ignore the fact that it's not exactly accurate, but it's just, I'm blowing it up so we can see what it is. So if we look at for the outside region, so you see we kind of have this rectangular region that we're looking at. Okay. Any questions there? Now, of course, you don't have to draw this. You can just basically deal with solving um, the inequalities. So the first one, if you have the absolute value of x minus 1 is less than or equal to 0.1. So that's basically saying that x minus 1 is bounded between 0.1 and negative 0.1. So add 1 to both sides. So I get 0.9 is less than or equal to x is less than or equal to 1.1. So that tells us that x is bounded between 0.9 and 1.1. And we can do the same thing with y. So we have that y minus 2 is bounded between negative 0.1 and 0.1. Add 2. So we get 1.9 is less than or equal to y is less than or equal to 2.1. So this is the boundaries for y. Here's our boundaries for x, okay, based on the information that we're given. Any questions? Okay, so if we want to find the error, so this is what we're going to do, okay? So the error is going to be less than or equal to 1/2 capital M times the absolute value of x minus x of 0 plus absolute value of y minus y sub 0, and this expression is going to be squared. Okay. Now, M, what it stands for is the max of basically the second order partials. So the max of f of xx or f of yy or the absolute value of the mixed partial. Okay, so whichever one of those gives me the maximum value, that is going to go in for M. Any questions? So what we need to do first is to go ahead and use the information that we started off originally. Okay, so we said that the mixed partial, the partial of f in respect to x was equal to y squared minus y times the sine of x minus 1. So if I find the second order partial in respect to x, what would I end up with?
A negative y cosine x minus 1.
Okay, so negative 1 times the cosine of x minus 1. All right. So next, we said the partial respect to y, it was equal to, let's see, 2xy plus the cosine of x minus 1. So what would be the second order partial with respect to y?
Two x.
Yes. Okay. And then the last thing we need to do is to find the mixed partial. And we can do it off either one. We can do it off of the partial with respect to x or the partial with respect to y. It doesn't matter. You're still going to get the same answer. So let's just do it off the partial with respect to x. So what would be the mixed partial? Yes. So it'd be 2y minus the sine of x minus 1. Okay? So we have all our partials. Okay? All right. Any questions there? Okay. So here's what we're going to do. Okay. So let's start with the second order partial with respect to x. Okay. So we said that f of xx, we said that was equal to negative y times the cosine of x minus 1. Okay. So what we're going to look at is if we take a look at 0.9 comma 1.9, and then we're going to look at 0.9 comma 2.1. Okay. Now, keep in mind what we're looking at is the endpoints, and we do have two other endpoints. So we have the 1.1 comma 1.9, and then we're going to have 1.1 comma 2.1. Okay. Now, the reason why I'm ignoring the second two is because of our property for cosine. Okay. And our property of cosine basically says that if you do the cosine of a negative angle, that's equal to the cosine of the positive angle. Okay. So it's the fact that it's cosine that we're allowed to do this. If it was sine, we would need to check all of them. Okay. So I don't really care about the 1.1 because it's going to get a positive 0.1. If I do 0.9, it's going to give me a negative 0.1. By the odd and even identities, it's the same value as far as cosine is concerned. Okay, so that's why I'm not really worried about these other two because I know it's going to produce the same value. Now, if I evaluate the function at these values, what will I get? So if I evaluate it at 0. You do need your calculator, and it needs to be in radians. All right, so if you put in 0.9, 1.9 into the second order partial in respect to x, what value do you get? Okay, you are going to get a negative, but just one thing I do want you to keep in mind that you notice that when I defined m, we are going to look at this in absolute value. Okay, so we're going to look at it as 1.89. Okay, now for the second one, what did you get? If you evaluate it at 0.9, 2.1. Yeah, so you're going to get about 2.09. Okay. All right. So we've checked all the, and like I said, if we did these other two, we're going to get the same values uh, back over again. So there's no need to really check those. Okay. All right. So now what I want to do is I've done it for the second order in respect to x. Now I want to do it for the second order in respect to y, which we said that the derivative for that was 2x, and it's not x. Okay. Now, here's the thing. The second order partial in respect to y is only defined in terms of x. Okay. So what x value is going to be the largest value that I'm going to look at? 1.1. Yeah. So I don't care what the y value is, it's just the x value that is concerned. So for this, the second order partial in respect to y, it's going to have a value of 2.2. Okay. Any questions there? All right. So now the last thing we're going to do is take a look at the mixed order. Okay. So with the mixed order, we have to be careful this time around. Okay, so for the mixed order partial, we got a value of 2y minus the sine of x minus 1. Okay, now keep in mind that we do have four values. So we have 0.9 comma 1.9. We have 0.9 comma 2.1. We have 1.1 comma 1.9, and then we have 1.1 comma 2.1. Okay. Now, the way I'm going to do this, I'm going to be cautious about how I do this. Okay. And now we have to understand that we are dealing with the trig function sine. And with sine, we know that if we do the sine of negative x, what is this equal to? So we know that the sine of negative x is equal to what? So it's going to be equal to the negative of the sine of x. Okay? Because sine is an odd function. So with that in mind, which is going to produce a bigger value for sine? is it going to be the smaller number or the bigger number? Why do you think the bigger will produce a bigger value? Yeah, it's actually going to be the smaller, and here's why. Okay, if you use the bigger, that means that this angle is going to be what? So if I use 1.1, that means the angle is going to be what sign? Positive or negative? If I use 1.1, it's going to be positive. So since it's positive, is it going to change that sign? No. So that means I'm going to be subtracting. So essentially, it's going to make the value of f of xy smaller. Okay, so that's why I'm going to ignore these, because it's actually going to make the value smaller. Okay, whereas if I put in 0.9, this is going to make this negative. Okay, but by the odd and even identity, it's going to make it the angle positive and the sign in between them positive. So it's going to actually make it larger. Okay, so this is why I'm only going to look at these two. All right. So now, if you evaluate for the first one, let me see what we're going to get. So we have 2 times 1.9 minus the sine of negative 0.1. And this is going to give me 3.9 for this. For the second one, it's going to give me a value of 4.3. Okay. So now I've gotten all my values for each of all the second order derivatives. So here are the values that I have. I have the value of this, I have the value of this, I have this value, and then I have this one and this one. Okay, so looking at all of these, what's the maximum value? Yes, so 4.3 is what I'm going to use in the error formula. Okay, 4.3 is what I'm going to use in the error formula. So when I fill that in, so the absolute value of the error is going to be less than or equal to 1/2. For m, I'm going to use 4.3, okay, times. Now, notice that in the formula, I've got the absolute value of x minus x of 0. Okay, and then I've got the absolute value of y minus y sub 0. All right, so what is the largest that the absolute value of x minus x sub 0 can be? It won't be 0.9. What's the largest that the absolute value of x minus x of 0 can be? And this little part is a little sneaky. Okay. It actually, if you look at this, x minus x of 0, the largest it can be is going to be what? 0.1. Okay. And then y minus y sub 0, the largest it can be is going to be what? 0.1. Okay. So basically, that portion of the error formula, you're going back to the region and seeing what the absolute value is less than or equal to. And that's going to be the largest it can possibly be. And you always want to use the largest possible value that it can be. So in here, we're going to have 0.1 plus 0.1, and then we're going to square that. So if we do this calculation, we're going to get we're going to get this value is going to be approximately 0.086. And let me double check and make sure I did that calculation correct earlier on. Yes. So it's going to be approximately 0.086. Okay. So this is how much error it's going to be for the linearization, okay, within this small bounded region. So if I choose any point within that bounded region to basically in that rectangular region to approximate f of xy at that point, I'm going to be off by this, okay? And it can be plus or minus, okay? Because we're looking to error an absolute value. Any questions? Okay, so we're going to stop here for today, okay? Please make sure that you have been, you've worked on, I'm gonna look at it real quick. You've worked on the directional derivative and gradient vectors. Make sure you've worked on the homework. I do have the solutions posted for that, so you can check those. Also, you need to start working on the tangent planes and differentials homework also. Okay, and again, just keep in mind this stuff, all this, what we're doing now is material for the final exam, but you do need to keep up with this and everything because you'll be starting to have some quizzes over that and everything. Now, do you remember that the midterm is next week? The midterm is next week. Any questions? All right. Well, that is it for today. You guys have a great rest of the day, and I will see you tomorrow. I mean, see you on Thursday, not tomorrow.
You are currently the only person in this conference.